I'm going to talk about today, and that is this connection between the Jacobsville sandstone and the Portage Lake volcanics. And what's really nice also that I like about this photo is that it showcases a good portion, if not almost all, of the Gratiot Lake Conservancy that's at Gratiot Lake. So I've always liked this one. Moving forward, so we're going to start with a little bit of background here. Now, the bedrock that we see at the surface today, here in the Keweenaw Peninsula and in the greater Lake Superior Basin, are present thanks to three really important geologic mechanisms. And this is rifting, shortening, and glaciation. Now, first, we have this enormous rift system that we call the Mid-Continent Rift. It is believed that over 1 billion years ago, magma from the Earth's liquid mantle began to rise and pond up underneath the Superior Craton, which is now known as the North American continent where we live. Now, when I think about mantle plumes, I often imagine a huge lava lamp where the wax that's inside the lava lamp, AKA the lava, gets heated up from below and then rises, kind of morphs around, sinks, and then repeats. Well, this is similar to how mantle plumes end up behaving. So the emplacement of this hot magma close to the Earth's surface caused weakening of the continental crust. And then the rift generates a breaking apart and creating this area that I'm going to bring out my laser pointer real quick. So you can see in this, you see, yeah, you do see that. Okay, good. I wanted to make sure. It breaks apart the continental crust in an extensional regime, allowing for lava flows to start pouring out onto the surface. And now these are not just normal lava flows. These are oceans of magma that are reaching. These are some of the largest lava flows on Earth. In fact, the Greenstone flow is the largest lava flow on Earth by size or by thickness and volume, which is kind of an interesting little tidbit you should keep in the back of your head. Now, as the lava cools, when it's at the surface, it becomes a basalt. This is a super dense, very dark rock that we're all very familiar with up here, at least in Keweenaw. And it is believed that the regional tectonics at the time were in extension. So that means they're breaking apart. And the rift is then bounded by normal faults, which I will get into a little bit later in the talk. But it's bounded by normal faults. So the stuff in the middle began to sink and subside. The weights of these lava flows was so dense, so heavy, it creates kind of this bowl-like feature, which we call a syncline, which is actually the Lake Superior syncline, and it's maintained this for over 1 billion years, which is pretty incredible considering the amount of geologic time that is. Now, it is also believed that the regional tectonics flipped from an extensional regime to a compressional regime during the rise of the Appalachian Mountains and the Grenville erosion. So these are mountain building events where continents are coming together and they're hitting each other, pushing things up. And what we see is that the stuff that got down dropped in the normal faults gets thrust up and over onto younger. So this is kind of, we're going to get into some of the more fault stuff here in a minute, but as we move forward into the last 10,000 years, the Lake Superior region has experienced 4 separate glaciation events. This is advances and retreats, which have kind of really sculpted and formed the landscape that we see at the surface today. Now, differential erosion is simply the fact that some of these rocks are more resistant to weathering and erosion than others. And so as the glaciers scraped their way across the land, they physically removed weaker sediments, softer sediments, and weaker rocks. So here in the Keweenaw Peninsula, we have 2 primary geologic formations of interest, and that's the Portage Lake Volcanics and the Jacobsville Sandstone. Now, the Portage Lake Volcanics consist of over 400 individual basaltic lava flows, and each one of these lava flows is interbedded with lithic sandstones and brecciated flow tops and conglomerates. These sedimentary layers help us correlate these lava flows across space and actually time. Now, radiometric uranium lead dating on the lava flows itself leads us to understand that these are 1.1 billion year old rocks that are at the surface. Again, the glaciers came out, they scraped everything away that was on top, revealing these amazing rocks that are a billion years old. Now, while their age and extent and exposure at the surface is impressive, the more important fact is that these lava flows hosted an economically significant native copper deposit to the likes the world has never seen. Now, due to this economic interest, these rocks have been studied very well, actually very extensively for the last 150 years. The other geologic formation that we're going to be talking about today is the Jacobsville sandstone. Now, for the technical, the geo nerds out there, this is a feldspathic to quartzose mature sandstone that has red siltstone and shale facies interbedded, but it is distinct because of the redness and the whiteness that you see. And it is believed to be sourced from the remnants of a mountain that was a mountain building event called the Pinocchian orogeny that was much older than the rocks that we're looking at now. And the Jacobsville sandstone is easily identifiable because of this rusty red iron stained rock. And it has these very stark contrasts with these white spots or white layers like you see here in this photo, thanks to Steve Brim. Now, this sandstone can range anywhere from 100 meters up to 900 feet in some sections. And so, but the beauty of this was really sought after. I mean, this stone is striking. You've seen it. If you've been up to the Keweenaw and you've seen some of these historical buildings, you know that they've used it as accent pieces on all of these historical buildings up here because it's gorgeous. Now, the one thing about the Jacobsville, it makes it kind of, let's say, troubling to geologists, is that there's no fossils. There's no datable minerals. There's actually no cross-cutting relationships with igneous bodies that allow us to date these rocks. So the age of the Jacobsville is really poorly constrained. So we know this. We know that it is younger than the Porter's Lake volcanic lava flows, but it is older than the Munising Formation, which occurs just to the east in the eastern part of the UP. And the Munising Formation has been dated. It's been dated to about 542 million years old, which this puts a window of about 500 million years on the age of the Jacobsville. Now, in geologic terms, that's enormous. There's so many things that can happen in 500 million years. But in general, the Jacobsville is flat-lying, except where it has come into contact with the Keweenaw Fault. This interaction between the fault and the Jacobsville has created some really spectacular geosites, including the Calumet natural wall, which I have featured here in the lower right-hand corner. Now this wall, and I've been out to this site now twice, it's spectacular. You think somebody actually made it. Someone brought blocks of Jacobsville sandstone and stacked them up and put them, but it's not. This is actually in place. And I did a couple measurements and it's even overturned. So these are vertical. That means that the fault had folded and bended these rocks up into a vertical position from a horizontal surface. Now, before we get into more fault details, I want to make sure everybody's on the same page with some of the structural geology. So I'm going to give you a little quick crash course in structural geology. And I mentioned these terms, you know, normal faults, reverse fault, thrust fault. So there are 3 end member terms that are used to describe faults and classify faults. And this is normal, reverse thrust, and strike slip. Normal faults occur under extensional regimes, just like the mid-continent rift. In the case of the rift, the crust pulls apart and there's a center block in that rift that gets down dropped and it falls down. So it appears that the younger rocks on the flanks of the rift are above the older rocks that have been down dropped. In a reverse or a thrust fault setting, this occurs during times of compression, like a continental collision or a mountain building event. Now, as the Earth squeezes the crust together and our previously mentioned down dropped block gets forced up and over and on top of these younger sediments. Now, both normal and reverse faults are considered to be dip-slip faults. And this means that the rock moved up and down based on the angle of the fault plane. So in these figures I have here, this would be the fault plane. And in a normal fault, the hanging wall falls down, where the footwall appears to remain stagnant, but it's technically up. In a reverse fault, again, the fault plane, hanging wall has been pushed up and over the footwall. These terms can kind of get confusing, and I have tried to find ways. So the best way I can remember how to these terms is for a hanging wall is that you can hang somebody from the hanging wall. The footwall is where your foot is. That's the best way I can come up with it. If you can come up with a better one, you let me know. Now, in contrast to the normal faults and the reverse faults, we have strike-slip faults, like the notorious San Andreas Fault in Southern California, where the rocks of the same age are sliding past each other in opposite directions, and this is due to the translational tectonic regime. And by translational, I mean simply that continental plates are sliding past each other. I want you all to keep this in mind. This is very important. It is extremely rare to find a fault that is purely dip-slip or purely strike-slip. Most faults exhibit kind of a combination or degree of one or the other. And we usually term, when it is close to this about 50-50 split, we call those oblique slips. Now, before I move on, I want to make sure that everybody's clear on these kind of terms. And I also want to make sure that like the idea of strike and dip are kind of clear. And something that I harnessed from, I think, every structural geology and intro geology class is this little house diagram here that shows kind of this example of what a strike and a dip is. So the strike would be the roof line, and the dip would be the perpendicular from that roof line. And the dip angle would be the angle between the horizontal and the plane, the fault plane. But if you have more questions, please let me know and I can clarify them. So I'm going to continue to move forward. So I'm going to give you a little brief overview of the Keweenaw faults before we get into some of the more specifics of our mapping. So this is an impressive fault. I mean, in fact, it's the largest structural feature in the Lake Superior region. This fault stretches 250 kilometers on and offshore. And it has been described historically as a reverse fault with up to 9 kilometers of net dip slip. So that means it's slipping along that plane, that fault plane that we mentioned earlier. Now, as I mentioned in the first slide, this fault serves as the geologic and topographic boundary that juxtaposes older Portage Lake volcanics above the younger Jacobsville sandstone. Now, as I mentioned, the Portage Lake volcanoes, they largely consist of these basaltic lava flows with smatterings of intrusions and these interflow sediments. Whereas the Jacobsville sandstone is these red and white sandstones. So it's very obvious to see in photos and aerial photos and in the field. And I have this great photo here from the Lake Superior shoreline viewer. And you can see this is behind here, this is all basalt. And this is all Jacobsville sandstone. And I have actually been out to this site. I have been on the boat capturing these points for a previous mapping project, which I'll talk here in a minute about. But it is very obvious when you see these two very different rock types in contact with each other. Many Lake Superior geologists suggested the most important feature of the fault was that it provided a fluid pathway for copper-bearing fluids to get up and migrate and then deposit this amazing world-renowned copper deposit that we have here in the Keweenaw. That's why we call it the copper country. However, a lot of research, a lot of boots on the ground mapping was needed to actually formalize these concepts of the Keweenaw Fault. So the concept about the contact between the Portage Lake volcanics and the Jacobsville sandstone has evolved over time. There's been a lot of debate, but the earliest iterations date back all the way to 1840. The Keweenaw Fault was formally recognized and defined by Irving and Chamberlain in 1885. Now, these observations that they made still hold merit today, and we will talk about that. Irving and Chamberlain, were the first to note that the Portage Lake volcanics have been thrust on top of younger Jacobsville sandstone. At the time, they were calling it the Eastern Sandstone because they didn't have the Jacobsville name. Based on their observations, Irving and Chamberlain theorized that the lava flows were upturned into their current northwest dip position, faulted, and then partially eroded prior to the deposition of the sandstone. And in addition to that, the Jacobsville sandstone would then get unconformably deposited on top of the Portage Lake volcanics in certain locations. And what I mean by unconformably is that there's a missing block of time between when the lava flows cooled and became rock and when that sandstone first appeared on top of them. So there's missing time. That's what an unconforming basically means. The Irving and Chamberlain also believed that there was subsequent minor faulting that occurred along these old fault lines. These reactivated faults deformed and contorted the contact edges of the sandstone in certain locations. So in other words, back in the 1880s, two very intelligent gentlemen believed that the Keweenaw Fault moved at least twice, once prior to deposition of the Jacobsville and again post-deposition. Now, as we fast forward to the 1950s, the USGS initiates a major mapping campaign. And this thing synthesizes mining company data, which was proprietary and very held close to the chest at that point, geophysical and gravity magnetic surveys, and intense boots on the ground bedrock mapping. The terrain here is challenging. The field season, limited, and the bugs, atrocious. But even more confusing is the field relationships of these two rocks. Despite these challenges, the USGS published a set of beautifully detailed bedrock quadrangle maps for the area. But there's a problem. These maps depict the Keweenaw Fault as a single, sinuous fault trace with anomalous geometries and puzzling, if not completely impossible, slip dynamics. Now, with the emergence of plate tectonics and advances in structural geology, new ideas and theories began to formulate about the Keweenaw Fault. And our current working paradigm suggests that the Keweenaw Fault initiated as a rift-bounding normal fault that was then reactivated as a thrust fault contemporaneously with the deposition of the Jacobsville sandstone. And most recently, mapping that's done by some of my colleagues up near Keweenaw Point and Beta Gree under the USGS EDMAP-1 project, Jim DeGraff and his students at Michigan Tech discovered a number of really interesting field relationships. They found that the Keweenaw Fault consisted of multiple segments that moved at different times, some with movements prior to the deposition of Jacobsville and others afterwards. Their field evidence shows unconformities, again, missing time, between the Portage Lake volcanics and the Jacobsville sandstone, which were previously not identified. And this implies that, again, the Jacobsville sandstone is going to be different in some of these locations. It's not going to be the same. These segments moved at different times. They moved in different ways. And so we're trying to really tease that out. One thing to keep in mind, the section of Jacobsville sandstone near Houghton is almost 2,000 feet thick. The section of Jacobsville sandstone that they observed up at near Keweenaw Point is only about 60 feet thick. So there is something interesting going on here that we need to figure out. Additionally, these MTU mappers on this USGS EDMAP-1 project found evidence suggesting of significant strike slip as opposed to completely thrust and reverse faulting. So what does all this mean? I mean, I've been talking for a little bit, and I feel like I'm contradicting myself back and forth. But what does all this mean? I mean, is it possible the Keweenaw Fault contains variable modes of slip? Could this fault be a series of segments separated by unconformities instead of a single sinuous fault trace? Well, that's exactly what my goal was to find out with this mapping project. So here's a big kind of more blown up map of the USGS quadrangles. And you can see there's actually a number of quadrangles here. We have Mohawk, we have Bruno Creek, we have Eagle Harbor, we have Delaware. And this little sliver right here actually was a kind of a subset map, and it's kind of a doozy to find. But I had to splice these all together using GIS, which is what I do. And I just want to point out that this thick red dashed line is what the USGS interpreted as the Keweenaw Fault. These little dotted red lines, these are interpreted fault splays from that fault. So maybe it's got some complexity to it. Sure, why not? Let's take a look at it. All right, so again, we've identified a number of anomalous geometries here. So starting with A, we have this kind of down drop block on the footwall side of the Keweenaw Fault. And it's Portage Lake volcanics? That's confusing. What's up with that? Area B, we have identified a fault splay junction, which we just wanted to make sure we got to and investigated to see if it actually exists. C, is an area that the USGS described as a major reentrant of Jacobsville sandstone. And here you can see this kind of horseshoe shape. It's really weird. How can a fault look like that? And then D, there's just some strange things going on. Changes in thickness of flows, this little offset fault, another fault splay junction. What's really going on here? So maybe this might be a good time for us to take a break. Oh, I didn't want to mention E. Area E was added later into the mapping project to kind of understand, to try to make an attempt to understand the relationship between the Keweenaw Fault and the Mount Bohemia, and the Bohemia intrusion, which is a completely different monster all in of itself. So the goal was to understand the fault splay and assess the nature of this anomalous Portage Lake volcanic fault block that was located in the footwall. And then at focus area C, we examined the nature of this really strange horseshoe-shaped geometry of the major reentrant. And now, before I get into the geology, I just want to very briefly mention some of the methods and the technology to make all this work possible. Our study was divided into two areas where there were two field teams assigned, one to the east, one to the west, with a graduate student primary mapper and an undergraduate field assistant. And then our primary investigator and expert mapping advisor, Jim DeGraff, would alternate between these two field teams. And he'd be providing training and instruction, help us take measurements, and also provide us moral support for when we're stuck in a swamp and there's no rocks to be seen whatsoever. But mapping here really involves boots on the ground data collection, specifically targeting these stratigraphic and structural relationships between these two, the lava flows and the sandstones. Where we paid particularly close attention for kinematic indicators like slicken lines, and just looking for evidence of like shear where rocks are moving past each other. While the tried and true analog methods of taking notes in a notebook and taking measurements with a Brunton compass, these two guys right here, these are amazing, these are timeless. But we supplemented those analog data collection methods with some digital data recording systems. Now these included the Trimble DGPS, which gets sub-meter horizontal and vertical precision, and then two smartphone apps, Avenza Maps and FieldMove Clino. Avenza Maps is wonderful because it lets you find yourself in the field even if you don't have cell phone coverage. And then FieldMove Clino is fantastic because this allows you to take bedding measurements and other kinds of measurements, even in the presence of magnetic anomalies or underhangs, places that the Brunton compass cannot physically get to. So these were huge in making this mapping possible. So the combination of this technology ensured for the quality and the consistency of our data collection, in addition to keeping us on target for when we lose ourselves to the woods which if anyone's been out to the Gratiot Lake Conservancy, it's very easy to lose yourself to the woods. Next, I'm going to go and share some of the findings that we made during the 2019 and 2020 field seasons. But so we were out there for about 2 weeks doing training, just kind of like, this is how you take a measurement. This is what a basalt looks like. This is what a sandstone looks like. This is how you record this stuff. And so I'm out there, I'm thinking, I'm like, wow, all of these outcrops, they're located specifically in certain places. What's going on here? So it was a fairly obvious, but it was a crucial discovery about how and where to locate these rock outcrops that safeguard the Keweenaw Fault's deepest held secrets. And the secret is all of these rocks are in the streams, and more specifically, streams with very steep slopes. So with my background in GIS, I did a little handiwork and quickly delineated a watershed for our field area and the Gratiot Lake area. Now, granted, you'll notice there are some streams on here that you may not be familiar with, like Creek 933. Yes, I did make that up creatively, named after Creek 932, which is an actual creek on the maps. But these creeks had amazing exposure of some of these rocks. And I'll show you in the next slide the correlation between our observation points and then my stream mapping. So again, from the comfort of my comfy office chair, I mapped the streams with the greatest slope that indicated the greatest potential for bedrock discovery. The pink and the red lines that you see indicated here indicate stream slopes with 20 degrees or higher. And we typically found the most bedrock outcrops on the streams with, I'd say, 25 degrees and higher, but you can see the correlation worked out pretty well. So this really provided almost like a foundation for where we're going to plant our targets and where we're going to go and look for these things. The steeper the slope, the more likely the presence of bedrock holding up that stream. And strangely enough, we did manage to find outcrops in the least likely of places, and that's the flat, low-lying meanders of the Little Gratiot River, just to the east of the Gratiot Lake Conservancy. So you can see these dots down here in this Little Gratiot River. Those are brand new data that no one's seen. There's nothing mapped there. It is awesome. This is all kind of groundbreaking stuff. And we found basalts, and we found sandstones, and we found sandstones that had been tipped up on end. What do we got? I don't know. A fault maybe? We'll get to that. But I also want to mention quickly that, fieldwork has its dangers, and even though you're mapping in a flat, low-lying, slow meander of the Little Gratiot River, you can still tear your ACL, which I unfortunately did last field season and have since recovered and am ready to be back out in the field this summer. So now moving forward into some of the findings. Now, if you recall a couple slides back at Focus Area A, this is located at an anomalous Portage Lake volcanic block in the footwall of the Keweenaw Fault. The USGS mappers identified this block through an aeromagnetic survey, which indicated that there was magnetic material, i.e. Portage Lake volcanics, in the subsurface. So instead of going out there and ground truthing this, they just drew a red dotted line around it and called it a fault splay, and they moved right on. But moving on to our modifications, we believe that there was an erosional unroofing of Jacobsville sandstone during the last major glacial retreat, which exposed two very important structural elements in this area. And that is, one, an unconformity, again, missing time, and thrust fault splays. Sections of the fault that have, smaller sections of a thrust fault. Thrust faults commonly are associated with multiple splays, depending on the timing and how things actually contract. Now, the unconformable contact between the Portage Lake volcanics and the Jacobsville sandstone in the footwall, as indicated by the blue dashed line here, is inferred based on the geophysics, but also ground truth in diamond drill hole logs from Deer Lake. The DL4 and the DL5 diamond drill hole logs reveal that there's a very thin layer, horizontal layer of Jacobsville sandstone directly on top of Portage Lake volcanics. There is also less than 60 feet. The Jacobsville here at DL4 is less than 60 feet thick, which is considerably thinner than the 2,000-foot section that's observed near Houghton. Now, this supports the notion that the Jacobsville was deposited unconformably on top of the Portage Lake volcanics prior to fault movement. And based on the available data, we believe that unconformity dips shallowly to the west. We also identified these fault splay zones that we have shown on the map, and that would be this splay and this splay here. Now, the last item that I want to point out in focus area A is the synclinal folds. And this is something that the USGS failed to recognize. But we have folds that are located here at the juncture between the unconformity and what we are calling the Keweenaw Fault. In addition to, and I'll show you this later in the summary map, but we also found folds associated with this thrust splay, and that was much later in the season. In fact, I only got to make one visit out there before I had my accident. So I will be going back and revisiting and remapping some of these points out there so that we have really good control on these things. But we have excellent samples in the lab right now, and I'm currently working on making a stratigraphic section for the Jacobsville sandstone at that location. And of course, I wanted to save the most dramatic map change for the last. Now, as we move further west down the fault trace, we encounter what the USGS termed the deep reentrant of Jacobsville sandstone. This crazy horseshoe that just does not look physically possible that it could exist. Now, one of the theories about this area is that glaciers came and they eroded through the Portage Lake volcanics, exposing this. So the fault that we see is actually a plane that we see that's been eroded through, which has a little bit of merit, but we were able to actually contest that with our field data. We discovered Jacobsville sandstone outcrops that were well within the mapped area as Portage Lake volcanics. And these are these series of outcrops right here. This actually is the fault going right through because we have Jacobsville sandstone and we have Portage Lake volcanics within, I'd say, maybe 10 meters of each other. So it was fantastic. This was one of the greatest discoveries, and it completely changed the map. And we start to really think about how these things are moving, how these rocks are moving. And then we started to look at this and compare it to the previous EDMAP project, which down here I have an example from EDMAP 1 of one of these orthogonal fault junctions. And also they also have that unconformity here too. But these orthogonal fault junctions have become a repeated pattern throughout our EDMAP projects. We started with EDMAP 1 where I was a field assistant. I was the lead mapper in EDMAP 2, and I will be a consultant on EDMAP 3, which just got funded and approved for starting this summer. Anyways, moving on. These new outcrops that we discovered up here pushed the Keweenaw Fault 400 meters to the north. And that's incredible. It just completely changed the map. Now, we also observed, similar to area A, we observed folds, but we observed both a syncline, which would be like a sink, and an anticline, which would be like a dome, and in the Jacobsville sandstone here. And these are spectacular exposures. I have a couple photos at the end that I'll show you that kind of showcase that. Now, the previous mappers who were mapping between Keweenaw Point and Beta Group Bay identified unconformities with these orthogonal splays. And the geometries really are quite similar to what we found. In fact, I believe that they're birthed from the same tectonic animal. And considering that Bear Bluff, where this map is actually taken from, is only 25 kilometers to the east, they likely are birthed from the same tectonic animal. So, coming back, this is kind of a little bit of a focus area on just the Gratiot Lake and seeing a kind of a before and after. Now, there's a lot of stuff, and we'll get into the summary map that'll kind of be a little bit more specific. This hatched area that I have here, this is actually the boundary of the Gratiot Lake Conservancy. There is a little bit more up here towards Lizzadro Farms, the Baumert Farm, but this is the area I wanted to focus on. And as you can see, we have these fault splays, we have the Keweenaw Fault, but we have folds in our new maps. There's no folds here. In fact, there's very few outcrops even maps. Each one of these dots represents a field observation. And I think when it came down to it, we were over 2,400 field observations for 2 field seasons. So this is incredible. I mean, I think on Sucker Creek alone, there's probably over 100. It was intense. It was intense mapping for sure. Again, the biggest contrast between what the USGS did in the 1950s and what we did just this past 2 years is the fact that we found fault-related folds and we mapped them in detail. So this is going to bring us to our summary map. And there's a couple things I want to point out here. You know, from the bedding measurements and the kinematic indicators that we were able to identify, it is safe to assume that the shortening direction or the compressional forces that were acting on the fault were oriented in a roughly southeast-northwest direction, as indicated by these red arrows. The Keweenaw Fault contains variable modes of slip along the entire thing. I mean, this is not a single fault trace, definitely not. I mean, you can see there's a mix of different symbols here. We have these arrows with on the black lines indicate a thrust fault. When you see these arrows kind of pointing opposite directions with a UD, this is indicating strike slip. And then of course, if you have these 2 different fault modes and they're joining together, there is a huge oblique slip that's interpreted in between. Structurally and kinematically speaking, this is a very complex fault system, but it is beginning to make more sense. However, there will be more structural analysis and cross-sectional work that is going to be forthcoming when I produce my thesis. I couldn't give you all the goodies. I'd have to make you come back for more. So what did we learn? Well, the relationship between the Portage Lake volcanics and the Jacobsville sandstone is much more complicated than we previously thought. The Keweenaw Fault is not a single sinuous fault trace, and it is not purely reverse thrust fault, as previously believed. We have significant evidence for unconformities in west of Lac La Belle, thanks to the erosional unroofing of the Jacobsville sandstone. Thanks to the glaciers. Yes, thank you, glaciers. And in focus area A, formerly known as the major reentrant, we have changed the geometry to make kinematic sense. Again, suggesting that there's nearly an orthogonal intersection between faults, and these are all based on ground truth field observations. However, the biggest contrast, again, I'm going to mention this, is that we found fault-related folds. This is something that no one else has done in this area, and this is huge. And while a detailed structural analysis is coming, we have solid evidence that there are multiple components of strike slip, oblique slip, and thrust in this area. And the best part for me is that I'm able to validate the claims that Irving and Chamberlain made back in 1885 that the Keweenaw Fault moved at least once, it moved at least twice, and there are unconformities present in this area. Now, as a fun side note, we found a dozen waterfalls or more. I mean, dozens of them. It was ridiculous. Anytime we found an outcrop, it was another one. So let's see. This is Sucker Creek. This is Bruno Creek. This is not a waterfall, but I think this one is also. I think this is one of the smaller sets of Snake Creek. I wasn't able to find my big Snake Creek falls. It's a huge waterfall. I think it was like a 60-foot fall. One of the biggest in the peninsula. So it's one of those things, it's one of those secrets that we get to keep. And in the Gratiot Lake Watershed, there's a ton of these things. And that's why this area is so amazing and so special. And I love it. So at this point, I'd like to open it up for questions and comments. And again, if you have more specific questions that you don't want to ask me right now, feel free to email me. I'm happy to share my email with all of you. I'm very accessible at Michigan Tech. So